You've been doing this series for quite a long time now. Luca was telling me.
Well, is it already a couple of years?
Yeah, we started in 2021.
Yeah.
2021 April.
Yeah, it was some random stuff. No, it was not actually random because Luca and Stravan, they were doing some online workshop. And after this workshop, which was very, very interesting with a lot of nice people, decided to continue the trend. Anyway, it was pandemic, but still, especially for people like me, mostly in China, it's a good opportunity.
Yeah, that's true.
Well, even though for China, it's a bit late.
Well, yeah, they are, how many hours difference?
With Europe, 6.
6.
Well, it's not extremely, well, just today I'm happily in Europe, but normally it's like late. Yeah.
Okay, I think it's a time. Maybe we can wait a couple minutes more because people are coming last moment.
Even Luca didn't come yet.
Yeah, he said he was stuck in traffic.
Yeah. No, of course, we are not obliged to wait for him, but still 1-2 extra minutes for bad students who come late.
Okay.
Yeah.
Well, it's just 5 just now.
Alexei, and whom we are waiting for?
No, I don't waiting for anyone specifically. I just was joking that Luca is not here yet. He's in the traffic.
Okay.
In Italy. Italian traffic, I remember. It's
that can be quite bad.
Very special, yes.
Even though he's not in Rome, I say no, still.
Yeah, well, even in southern Italy, it can be quite bad. So, I don't know where he's specifically at this moment.
But it's okay.
Okay, 30 people already. Maybe we can start today. Hello, everybody. Today we have a talk by Gulia Gubitosi. She will tell us about Planck's K-violation of Lorentz symmetry and their implication in astrophysics and cosmology. Julia, 1 hour, please.
Yeah, thank you. So thanks for the invitation to speak in this seminar series that I've heard is being very successful over the last couple of years. And thanks to the organizers for having me. What I'm going to talk about is mostly related to phenomenology of quantum gravity, and in particular its applications in astrophysics and in cosmology, as the title says. So I will start with a very short introduction about what we do in quantum gravity phenomenology, and then I will go a bit more into details. Okay, this is going through. Okay, so first question is, where do we expect to see any signal for quantum gravity? And well, we don't have a specific answer coming from rigorous derivation. I mean, it depends on the theory of quantum gravity that we want to consider, but we can make some general considerations. So you all know that in quantum gravity is the theory that should put together general relativity and quantum mechanics. And yeah, the difficulties are that in general relativity, we treat space-time as a dynamical entity and matter as classical. And this holds for macroscopic systems. On the other hand, the quantum mechanics that deals with the microscopic realm has a fixed background space-time and quantum matter in it. So both space-time and matter are treated differently in GR and in quantum mechanics. And you can see this very clearly when you think about how you localize space-time in the two theories. So in general relativity, you want to have a low mass probe so that it doesn't interact too much with the space-time and you can localize where it is. And this localization limit can be given in terms of the Schwarzschild radius. On the other hand, in quantum mechanics, localization becomes better if you have a high mass probe, so that you minimize the quantum uncertainty of the probe. And this scale of localization is given by the Compton radius. So you see that these two radii, one depends linearly on the mass and one depends as an inverse proportionality to the mass. And where do they meet? So where do we expect that the two theories talk to each other? It is when these two radii take the same value, and this happens for masses that are of the order of the Planck mass, which is 10 to the 19 GeV, or equivalently for length scales that are tiny, 10 to the minus 35 meters. So this is just an order of magnitude estimate, as I was saying, and you can expect that quantum gravity effects happen few orders of magnitude above or beyond or below these values. Think, for example, about theories with large extra dimensions. So because these scales are so extreme, for a long time, as you all know, quantum gravity was considered just a theoretical problem, and it was considered completely hopeless to look for any experimental signature. Think, for example, that if you wanted to test it with particle accelerator, then you would need a really large particle accelerator to reach Planck energies. So not possible to build it on Earth. You probably need the galaxy. And yeah, so for this reason, for many, many decades at this point, because quantum gravity has been a problem that was born when GR and quantum mechanics were born, basically, people have been focusing on building theories for quantum gravity and, for example, building many different pictures for how space-time should look at the Planck scale. And yeah, we've had a lot of proposals, perturbative quantum gravity, string theory, and so on and so forth. This is a very nice picture from the ISQG website showing, just giving an idea of how many different ideas have been proposed. So this was the situation until the late 90s, basically. So everyone was working on their preferred quantum gravity theory based on some assumptions that are reasonable, and each person would pick their favorite one. But then, as long as you don't have contact with the experiment, of course, you have the issue that you don't really have a way to choose which theory is the correct description of nature, apart from logical consistency and agreement with your preferences. So, as I said, this changed in the late 90s when it was realized that, in fact, you can access experimentally the Planck scale. And since then, there's been a growing number of people working on phenomenology of quantum gravity. And the crucial realization was that you do not need to reach directly the Planck scale if you want to test quantum gravity, but you can do something a bit different. So you can look for residual effects, for example, that happen that are still present at lower energies, and they could be detectable. This is one example. I'll give more examples later. So the difficulty of quantum gravity phenomenology, apart from the extreme scale that you want to test, is also that of all of these theories of quantum gravity, none of them, they're very complex, so none of them produces clear predictions about observations. I mean, you can think about some semi-classical effects that are inspired from quantum gravity theories, but like really rigorous derivations are not available, really. So for this reason, yeah, quantum gravity phenomenology is based mostly on studying effective models or deriving semi-classical effects from these theories. So get inspired from the full theories and produce some phenomenological models, which one can then test with experiments. And the idea is that you do this, and then based on the results, you constrain some classes of quantum gravity effects, and this informs then the development of the theory itself. So ideally, it should be a back and forth process that at some point converges to some quantum gravity theory. So what kind of, so first let me say, I mentioned here that quantum gravity phenomenology was born when we realized that we could access indirectly the Planck scale. And basically we can do it in two different ways. And the crucial thing is that we are, so what happened in the last 20 years, our observations of the universe improved really a lot. And the universe is what allows us to access the Planck scale. So first of all, it acts as an amplifier, meaning that if you consider, for example, propagation of a particle over cosmological distances, if this propagation is affected even by tiny effects, so governed by the Planck scale, still over a cosmological distance, this effect can grow significantly, so much so that it reaches a detectable level when the particle reaches Earth. The other thing is that the universe is expanding, and this means that it basically acts as a microscope. So when we, in the very early times of the universe, you could have relevant distance scales that were Planckian, and due to the universe expansions, these the Planckian distance scales become large today. And for example, if you look at the cosmic microwave background, then you have that this signal carries the imprint of the properties of the universe when the relevant scales were Planckian and then became macroscopic. So these are the two main things I will talk about in the following. Now let me discuss two features of possible quantum gravity theories that we can look for. This is, of course, not exhaustive. I mean, there are other things one can look for, but these are the ones I will focus on this talk. And if you want to hear about more, you can ask. So first feature concerns local symmetries of space-time. We can think that at the Planck scale, we do not necessarily have local Lorentz symmetry as we do see at our scales. And we have several options in quantum gravity theories. So either, well, yes, we can still have Lorentz invariance, or we can have models that explicitly break Lorentz invariance, meaning that we have a preferred frame, or we have models that are relativistic, so they do not have any preferred frame. However, the laws of transformation between different frames are deformed, and these are known as deformed special relativity or doubly special relativity model. Each of these assumptions, of course, will have different observational consequences, but I want to emphasize here that even within any of these assumptions, the predictions can depend on other features that one embeds into the model. For example, what are kinematical or dynamical assumptions, or whether you use Hamiltonian description for your theory, and so on and so forth. But let's say that these are three broad categories concerning the fate of Lorentz symmetry at the Planck scale. And okay, well, the first case is trivial, is what we already know. So let me briefly discuss what is the difference between breaking and deformation of Lorentz symmetries. As I already mentioned, when you are breaking Lorentz symmetries, you're basically introducing a preferred reference frame. And this can be, for example, a fixed background field. Usually these kind of models can be formalized at a phenomenological level in terms of standard model extension theories, where you are coupling matter or gravity field to extra vector or tensor fields. So here it's just one example of an action. Here would be the standard coupling to the metric, and then you have an additional coupling to some other tensor. And a typical manifestation of these Lorentz breaking theories is that the energy momentum dispersion relation of particles is deformed. For example, here is just one example. In the case of a photon, you may have the usual least square equal p square, and then you have a correction term that typically would go as some inverse power of the Planck energy if the effect is set at the Planck scale. Concerning deformations, So here you do not introduce any preferred frame, so you do not have any background field. Physics should still look the same to any observer. To think about this, you can think about what happened. So when you transition from Galilean to special relativity, you basically have two relativistic theories. So you do not have a preferred frame neither in Galilean nor in special relativity. However, in special relativity, you're introducing a relativistically invariant scale, which is the speed of light in this case. These theories with Lorentz deformations, you can think about them as a further deformation of special relativity of the same sort as the deformation that brings you from Galilei to special relativity. And here you introduce another relativistic invariant scale, which here is typically an energy scale, and namely the Planck energy scale. So what happens here, as I said, all observers agree on the physics. However, how you transform from one observer to the other is not according to, for example, Lorentz boost, but it is a deformation of Lorentz boost that is only relevant at high energies. I see there is something in the chat, but I don't see the chat. Well, maybe I go on, or should I stop?
Okay, Alexander, maybe you ask your question.
Was the idea of Lorentz symmetry breaking initially motivated by suppressing UV divergences by additional powers of momenta?
Well, there is also that motivation. For example, this is what happens when you do Rava-Lifshitz gravity. So there you're breaking symmetries, and that ensures that you have a renormalizable gravity theory. So that can be, yes, can be a motivation.
Thank you.
Sure. So in
sorry, in fact, there is some other question by Philip Mannheim, and if he wants to ask right now.
Oh, okay, okay.
Sure. Yes, good morning. With this expression plus or minus Xi over EPP cubed, you're allowing to go outside the light cone. I would have thought.
So you get superluminal propagation or subluminal, yes.
I would have understood you to say, well, okay, we'll allow for propagation either on or inside the light cone. But this seems very extreme. I hope you don't mind my saying so. To go outside the light cone.
Yeah, it is quite radical. And in fact, I mean, on this specific thing, there are very strong experimental constraints. So, but I mean, in principle, it is allowed within the theory. Then you have to see whether you can put constraints. And in fact, in this case of Lorentz breaking, superluminal propagation is really strongly constrained.
Okay.
For example, because if you have these, then you modify also. So if you have these, for example, you can have photon decay, which would not be allowed in a relativistic theory, but it would be allowed here. And because we see very high energy photons coming from far away, we know that this is not happening.
Okay.
So as I emphasized earlier, let me say it again. Here in these phenomenological models, you don't want to have too many prejudices concerning what is theoretically acceptable. I mean, of course, everyone has their own. You want to be as open-minded as possible and then let nature decide whether something is there or not. So it is a different approach from when you are building a theory, because there you want to think about whether something makes sense for you or not. Here you want to be as open-minded as possible. So as I was saying, when you have the formation of Lorentz symmetries, in fact, you can have, again, so this is a similarity between the two cases. You have also here modified energy momentum dispersion relations. So on this aspect, the two things are similar. Then, as I was saying, things become very different when you consider interactions. For example, I won't go in detail there now. If you have questions, then I'll be happy to answer them later. So here is just one brief slide saying, yeah, that
Tatiana, would you please, sorry, Tatiana, would you like to ask your question? Tatiana Pazdieva. Tanya Pazdieva asked the following question. What is a metric used in this article, in this action?
This action here? So the metric is
Yes.
some G mono. So this would be the metric. And then you would have that also you have some background additional tensor that couples to some of the matter fields.
So somehow tau matrix is independent of G.
It's not a metric because it doesn't transform as a metric. You have to think about it some background.
Some fixed background. Okay,
yes,
thank you.
Exactly. And that is what fixes the reference frame.
Okay.
Okay, so let me skip this. This is just saying that you may have any of these options concerning Lorentz invariance depending on the theory, but again, these are just indications, so I won't go there. And another thing I want to mention, besides the issue of Lorentz invariance, there is something else that we can look for in the theories and then test, namely what is the dimension of space-time at the Planck scale. So in recent years, since the early 2000s, basically, there has been a number of interesting results coming from different quantum gravity theories, suggesting that dimension of space-time runs with the scale. And in particular, it goes from usual dimension 4 at large distance scales to dimension 2 at small distance scales. These are theoretical results. Usually they're based on this notion of spectral dimension that basically considers some diffusion process in space-time and sees how the diffusion happens. What is interesting here is that when you have a running of the dimension, basically you can formalize it in terms of a modified dispersion relation of the same kind that we were seeing before when talking about Lorentz symmetries. This is because simply when you do this diffusion process, you have here a Laplacian, and then you represent a Laplacian in momentum space, and having a running of dimensions means that the Laplacian is deformed in a scale-dependent way. And when you do momentum space representation, then basically this reduces to a deformed, to a modified dispersion relation. Here is just one example. So if you have this dispersion relation here, so you have this extra term here where lambda, 1 over lambda is the energy scale of quantum gravity and gamma is some number. Then you get that at large scales, so for large values of the diffusion parameter, you have dimension 4 for space-time. Then you go to small values of the diffusion parameter, which corresponds to going to Planckian length scales, and the dimension runs from 4 to either 2 for gamma equal 2, or for example, 2.5 for gamma equal 1. Gamma equal 2 is the interesting value because it matches these results coming from more fundamental quantum gravity theories. Okay, so these are the two main topics I will talk about today. So because probably people are less familiar with the formations of symmetries, I wanted to give you, before going to the actual phenomenology, so to actual constraints, I wanted to give you one example of a model where you have the formation of symmetries. And this specific model is described in terms of quantum groups or of algebras. So this is, let me emphasize, this is just one mathematical framework to describe the formation of symmetries. It's not the only one. It is interesting because you have that when you consider matter coupled to 2+1 quantum gravity, then when you integrate away the gravitational degrees of freedom, you have that matter is this, so the symmetries of matter are described by some quantum group. This is the result of a number of works. And also there are recent results suggesting that if you take some Minkowski regime of loop quantum gravity, then again, the space-time symmetries are described by the formation of the Poincare group that again can be described in terms of a quantum group. So these are indications that this kind of model could emerge from more fundamental quantum gravity theories, even though these are preliminary results and more research would be welcome on this. So here I provide just one example of a quantum group describing the formation of symmetries, just to make something more specific. So what you do is you have commutators of your Poincare algebra. So here I'm doing just 1 + 1 dimensions for simplicity. So you have time translations, space translations, and boost. And you see that the commutators, you do not have a Lie algebra anymore because this is not linear. It's not linear. You have this nonlinear deformation here in the commutator between boost and translations. For compatibility of the structure, when you do this, so when you introduce nonlinearities here, you need to introduce some additional structure in your algebra, which is this that is known as coproduct, which basically tells you how to act with the generators on products of functions. So in the trivial case, which would be, for example, this one, you're just acting with Leibniz rule. And when you have these nonlinearities, then it means that you act with the deformation of the Leibniz rule. And yeah, because the algebra is deformed with respect to the usual Poincare algebra, that you also have that the Casimir of the algebra, which usually is related to exactly to the dispersion relation. This is also deformed in a nonlinear way. And this is what is especially relevant for the phenomenological studies we are going to discuss in a bit. So because the Casimir is deformed, then we have a deformation of the mass shell condition. Here is a plot of the mass shell condition for different values of the mass. So the blue one is for massless case. And here I'm writing the full dispersion relation, but also the first order deformation in terms of this kappa parameter, which is basically the Planck energy scale. So you can think about it as Planck energy scale. And you see that we have a deformation exactly of the kind that I was showing you in that previous general slide. Also notice that here, because of this deformation, you predict that you have a maximum value for spatial momentum given by the Planck scale. And from this structure here that I mentioned, which is the coproduct, you deduce that the composition rule of energy and momenta in interactions is also deformed. Well, here in particular is the composition rule of spatial momenta. And if you think about it, this makes sense, because if you're deforming the rules of transformations between observers, then the standard composition rule would not be covariant any longer. So you need to deform it in order to keep consistency and keep a relativistic framework. Here is just a note of folklore, but it might be interesting for some people. So these theories can also be described on momentum space rather than on space-time. And in that case, you find that the momentum space is a curved manifold with the Planck energy scale defining the radius of curvature of the manifold. And in particular, this model that I was talking about can be described in terms of a momentum space that has de Sitter geometry. So let's go to first step in direction of phenomenology. So we want to see how particles propagate in such a theory with deformed symmetries. So we just work out the word line for a massless particle, taking the Casimir as the Hamiltonian and using this as the to evolve coordinates. And well, surprisingly enough, we get that word lines are written in the usual way. So space equal time fundamentally. So you would say there is no effect. However, you have to take into account that because these symmetries are deformed, in particular, you have to account for the fact that the translations act in a non-trivial way of coordinates. And when you want to study propagation of a particle, you need to compare what happens when the particle is emitted, say at observer Alice, to what happens when the particle is detected, say at observer Bob. These two observers are in general related by a translation. And if the translation act in a deformed way on space-time, then you have that ALICE may emit two particles with different energies at the same time. They propagate, and when you do the translation to observer Bob, then Bob will see that these two particles arrive with some time difference, even though they were massless. So this is a general prediction of this framework, that you have that particles with different energies travel from source to detector and arrive at the detector with some time delay with respect to each other that is proportional to the difference in energy of the particles. Well, this is to the first order in 1 over the Planck energy. But we only are concerned with first order because that is already a tiny effect. So we are already lucky enough if we can test this. No need to worry for higher orders at the moment. So at the first order, this propagation time difference is proportional to the difference in energy and the length of and the distance of propagation. And eta is some numerical parameter, and this is just the Planck scale. So this effect sometimes is called the dual redshift because it's similar conceptually to the usual spacetime, to the usual energy redshift that is due to curvature in spacetime. This is a sort of redshift, but in time, so not in energy, and you can think about it as due to the curvature in the momentum space. So in this sense, it's dual to the usual redshift effect. One is due to curvature in spacetime, one is due to curvature in momentum space. So this kind of formula here is the starting point for phenomenological analysis, and now we go there. As I mentioned, you can get a similar thing also when you're doing Lorentz breaking theories. So from now on, I will not focus on deformed symmetries or broken symmetries. What I'm going to say holds for both of them, as long as you're just considering time delays. Then, as I said, you can distinguish them from other kinds of observations. But I think, I mean, for the moment, we can focus on this. So because we have this linear dependence on the time traveled and on the difference in energy, the ideal probe for this is to consider particles that propagate over very long distances. And for example, astrophysical particles are perfect. And also because you have this delta E, you want to compare the time of travel of a low energy particle and a very high energy particle. So this will amplify the effect the most. Of course, if you're considering propagation over such long distances, you can't really use this formula directly because this is in flat spacetime. You need to generalize it to account for redshift of energy, basically, so for curvature of spacetime. And so what the formula that you end up testing phenomenologically is this one here, where you see that instead of L times delta E, we have this function K that is a function of energy of the high energy particle and the redshift of the source, so the distance of the source. And you see that this function here, you can write it in terms of some sort of distance function that depends on your cosmological model. And for Friedman-Robertson-Walker model, this is the distance function that you are going to use, where H naught is the Hubble parameter, omega lambda, omega matter, density of a cosmological constant and matter. Let me also emphasize here that this is one possible formulas that is the one that is most used in experimental and phenomenological analysis. Other options are possible and depend on the details of your phenomenological model and also on the details of the cosmological model that you want to consider. But for now, let's focus on this one. And so what do you do? Well, there's been quite a lot of work on this in trying to test this formula. And recently, with this cost action that is a European network, and it's about quantum gravity phenomenology in the multi-messenger approach, We have written a very nice review that has the same title as the cost action and was published last year in this journal, and you can also find it on the archive. So I encourage you to go there for all the details and to know everything about this that was known until last year. Yeah, so there you see the first work was in the late 90s, and then there's been quite a lot of activity afterwards. And so this is a summary of experimental status at the moment. So if you test this formula, well, the one that accounts for curvature, but here I write this for simplicity. So when you test for these time delays using individual sources, so you compare the travel time of a low energy, so this is explained very schematically, then analyses are of course more complicated, but schematically what you do, you compare arrival time of a low energy and high energy particle coming from the same source, and you assume that they were emitted at the same time, or you account for what was happening at the source. So when you consider individual sources, at the moment we have constraints that are that say that this numerical parameter eta is smaller than 1. So this is great because we are really testing the Planck scale, and we are saying that up to this scale for a single source we do not see any effect. Here it's just one example of how you can do an analysis. You can compare different energy channels in which you observe a given source, and you see whether there is any feature in the time structure of these energy channels. For this specific study, it was very important that there was a very high energy photon with 30 GeV energy. And because this arrives basically at the same time as lower energy photons, so each of these dots is a photon, then you can set this kind of constraint. Notice that for this kind of energies and typical distance of these sources, so this is a gamma ray burst, GRB 090510, you expect that the scale of this time delay is tiny, order microsecond, let's say. But these experiments have the sensitivity to see such a small time delay. So very strong constraints have been put. Here, there is just one caveat to make, which is that when you consider one individual source, you are there is a degeneracy, possible degeneracy between the time delay effect and possible effects due to the emission processes at the source. So you can never be sure about when the signal you're seeing was emitted. So this is a caveat here. A way to solve this is to go beyond, so not to use one individual source, but to consider at the same time multiple sources at different redshifts. So because the time delay depends linearly also on the distance, then you expect that for the same energies, you expect the effect to be larger for larger sources, while on the other hand, you do not expect such an effect for intrinsic time delays. So this is one way to distinguish intrinsic time delays and propagation-induced time delays. So concerning different sources, there are just very preliminary studies at the moment. It is interesting because these preliminary studies give a different indication from here. So for example, there have been studies concerning putting together data from different gamma ray bursts that find some indication that there might be some effect. But again, here the big caveat is that it's very few data and these analyses can be refined significantly. But still, I think it's interesting to mention them because they provide motivation for going further and understanding this better. And concerning multiple sources, there has not only been studies with gamma rays, so concerning propagation of photons, but there have also been studies involving neutrinos. using data from the IceCube observatory. Neutrinos are important because they reach much higher energies than photons. So for photons, typically you have, in these studies, you are up to, well, lower than 100 GeV, around the tens of GeV. On the other hand, with neutrinos, you reach TeV and even PeV energies, so several orders of magnitude above. So they provide a complementary test because it's a different particle and also because you are in a different energy scale. And with these studies, you also get some indication that there might be something. Again, this is very few data points, so this might just fade away once more data points are added. But for the moment, this is what we have. Here are some technical details about how you do the analysis for neutrino. I will not go there now, but if you have questions, I can come back and say more about this. I just wanted to mention that something interesting is that if you put these two plots together in the same plot, you see you are many orders of magnitude separated in energy, but they look interesting, let's say. But again, this might be something that fades away in the next few years or not, but so stay tuned for more on this. So this is concerning searches for signatures of Lorentz deformation or Lorentz breaking. And I think I have another 15 minutes probably, and I can use this to discuss the searches for, so the implications of dimensional reduction, space-time dimensional reduction for cosmology. So what I discussed until now was using the universe as amplifier, as I said earlier. And what I'm going to discuss now is using the universe as a microscope. And so this happens because where you are in the early universe, as I said, you have Planckian wavelengths, typically. Because they are Planckian, they are very sensitive to any quantum properties of space-time. Then these wavelengths get stretched over expansion of the universe, and the perturbations with these Planckian wavelengths leave signatures in the cosmic microwave background. So typically you describe the information encoded in the cosmic microwave background via some power spectrum that tells you about correlation between different points in the sky, given an angular scale. When you compute this power spectrum, you have a contribution that really comes from the physics of the early universe, which is the primordial power spectrum. And then you have some transfer function that is pretty well understood and depends on the evolution of the universe since then. So it concerns, say, late time universe. And this part is very well understood. So if you look at the power spectrum in the CMB, you get information about the primordial power spectrum. And this is sensitive to, very sensitive to quantum gravity features. Okay, so in particular, what we know about this primordial power spectrum from observations of the CMB is that this power spectrum is scale invariant with a slight red tilt. So it has a very tiny dependence on the wavelength. But from, let's say, order 0, it is scale invariant. And usually this is explained by inflation. Here is in one slide how you go from primordial perturbations to scale invariant power spectrum. So you want to look at the evolution equation for primordial perturbations. So you have V is the Fourier mode of your perturbation for wavelength K. And you have that the evolution contains a pressure term and evolution due to gravity. At small length scales, you have that the pressure term is dominating, and at large length scale is gravity that is dominating the evolution. So to solve this equation, basically you can solve for the two regimes and then interpolate. and find what is the complete solution. Just notice here that what we measure is the moving gauge curvature fluctuation, this parameter zeta, that is related to the perturbation variable and the scale factor in this way. So the power spectrum, the primordial power spectrum, is defined in this way here. So when we consider the solution to this equation in the two regimes, and then we do the matching, and we consider the zeta inflation, so exponential expansion of the universe, what you get is that the power spectrum, so this variable V over A takes this form here, and you see that A factors cancel, and this K, so the wavelength contribution also cancels with this one here. So you get that the power spectrum is scale invariant. This is just standard inflationary cosmology. But so how does the dimensional reduction enter into this picture? To understand this, is important to remember what we said, that dimensional reduction is related, can be parameterized in terms of a modified dispersion relation. So in this case, it would be a deformed dispersion relation for the primordial perturbations. This is the ansatz that we can use. Again, we are considering, so lambda is 1 over the Planck energy, and gamma is that numerical factor that we have seen already. And let me remind you that for gamma equal 2, we get dimensional reduction to 2 in the UV, which is something that has emerged in several quantum gravity theories. So because the perturbations have Planckian wavelengths, they are sensitive to the UV limit of this modified dispersion relation. And I am emphasizing this because when you're doing this, when you're playing this game in the primordial universe, you are most sensitive to the UV limit of your dispersion relation. While I mentioned that in astrophysics, you are only sensitive to the first order correction of your dispersion relation. So you're really testing two different regimes of the same feature. So you cannot really compare results coming from one or the other. They give you different informations. So when you have such a dispersion relation, basically, you can say that the speed of perturbation becomes dependent on the wavelength and on the scale factor, because you write the physical momentum in terms of comoving momentum. And when you introduce this modified speed in the evolution equation that we have seen before, so it enters here in the pressure term of the evolution equation, and then you solve this equation exactly in the same way as you would do in the usual inflationary scenario. You get solution at small scales, large scales, and you want to do the matching to get the power spectrum. And you get that the power spectrum takes this form here. And you see that you have, again, scale factor and factors of wavelength. And something quite remarkable happens when gamma is 2. So with this special case that was special for theoretical reasons. Now it becomes special also for phenomenological reasons, because for gamma equal 2, the scale factor cancel. So you get a result that does not depend on the kind of evolution you have. So it doesn't depend on whether you have inflation or power law expansion or anything else. So you don't need inflation for this in particular. And you get that when gamma is 2, the factors of K also cancel. So you are left with a scale invariant power spectrum, independent on the background evolution. Okay, I showed this for this specific model here, but in flat spacetime, you can show that this is true in general when you have UV dimension equal to. And so this is interesting. And you see here that the power spectrum then is given by the ratio between the Planck length and this scale where the deformation of the dispersion relation is relevant. And this ratio basically gives you the amplitude of the power spectrum. And this is something that also we measure in the CMB. And we know that the amplitude is 10 to the minus 10, which means that if we want to match what we see in the CMB, then this scale lambda should be 10 to the 5, the Planck length. I mentioned that the power spectrum is not exactly scale invariant, but it has a red tilt. So in fact, you can parameterize it in this way with this NS, with an S smaller than 1. You can produce such a thing if you allow for a gamma not exactly equal to 2. And well, and so you can get this when gamma is within this range and you allow for different equations of state. So getting the red tilt actually depends on the equation of state, while getting the scale invariant case does not depend on the equation of state. But you get something of this sort. So this is interesting. And the last thing I want to say concerning this is that we played this game for scalar perturbations, which is what we have observed so far for the primordial universe. But you can play a similar game concerning tensor perturbations. So these are the ones that generate primordial gravity waves. Assuming that tensor perturbations obey a similar dispersion relation as scalar perturbations, but possibly with different lambda and gamma parameters, then you can constrain the value of the scale where tensor perturbations get the deformed dispersion relation using the tensor to scalar ratio. So the ratio between the amplitude of the tensor spectrum to the amplitude of the scalar power spectrum. Assuming that the power law for the two cases is the same, you get that the tensor to scalar ratio just depends on the ratio between the scale of quantum gravity for scalar and the scale of quantum gravity for tensor modes. Using the upper bounds that we have on the tensor to scalar ratio, you can get a lower bound on the scale of quantum gravity for tensor perturbations, which is given by this. Yeah, so I skipped some things during my presentation, so I will stop here. I thank you for the attention, and maybe you can ask me what you would like to hear more in detail.
Oh, thank you very much for your very interesting and informative talk. Questions, please. I see a question from Wu. Oh, yeah. Please ask your question.
Yeah. First, thank to the next talk. I have a question. What happened with gamma not equal to?
With gamma here, you mean?
What happened if gamma not equal to?
Yeah, so here what happens is that if gamma is different from 2, you lose this property of having a scale invariant power spectrum. So from the point of view of this kind of analysis, so if you want to use this dimensional running to explain a scale invariance of the primordial power spectrum, that doesn't work.
Yeah.
Because you would lose the feature.
This theory is this theory how to change theory.
Sorry, can you say that again?
How to change theory if
gamma is different than 2.
Yeah.
You mean to get again scale invariant power spectrum? I'm not sure. I mean, Within some range, you can try to adjust for the equation of state parameter and try to reproduce this result, but you don't have much space to do that. So, for example, here I show that if you really want to match the correct power law for the power spectrum, then gamma should be in this range here.
Yeah.
So yeah, I don't think you can get the gamma much different than 2 if you want to use it for this.
Okay.
Okay, let's go to the next question. The next question is from Betal. Dipan, please ask your question.
Yes, ma'am. Am I audible?
I'm sorry?
Am I audible?
Yes,
Yes, I can hear you.
Yes. So, is there any effect on any effect on the renormalization of any quantum field theory because of the change in the Lorentz in the Lorentz symmetry at the Planck scale? Means, will there be any kind of regulatory?
In principle, you can have that this when you introduce this Lorentz violation, it can help with regularizing your theory. And as I mentioned, I think in the beginning, one well-known example is Orava-Lifshitz gravity. So there you introduce an anisotropic scaling between space and time that is breaking Lorentz symmetries, but it is useful because it regularizes the theory in the UV. In that case, is the theory of gravity, of course. So it can help. And also these quantum groups, so they are related to non-commutativity of space-time coordinates. And in fact, models with non-commutative space-time coordinates, they were originally proposed in the late 40s, so a long time ago, when people had not developed the whole renormalization approach to quantum field theory. And they were introduced because people were hoping that having a non-commutativity in space-time coordinates could regularize the theory. Because fundamentally what you're doing, you're introducing some minimal length scale. So it's kind of a cutoff. So also in that case, you might have effects on the renormalizability of your theory.
And does it show any effects in the primordial spectra if we consider some matter coupled with the gravity and we observe the spectra and on the CMB? Should there be any effect expected versus?
Well, for primordial perturbations, you care about what space-time perturbations do. You don't care about matter yet at the time. Again, for example, these kind of studies have been done also within Orava-Lifshitz gravity. And it is interesting because there is a special case of Orava-Lifshitz gravity that is also the case where, well, it was much before, but yeah, so Orava gravity with critical exponent 3, which is a special case for theoretical reasons, is also the case that produces this running to 2 dimensions in the UV, and it would be the case that would produce this scale invariant spectrum. And this has been shown in a paper by Mukoyama, I think, not using this technology of dimensional running that I was discussing here. The computation was done within Orava-Lifshitz gravity. So in some sense, it is a complementary result that goes in the same direction as this one that uses dimensional running.
And is there any effect on the unru radiation because of the change in the Lorentz term? Maybe at different lower.
Sorry, can you say again, because I didn't get you.
Is there any effect on unru radiation because of this curvature in the momentum space?
There might be. You mean unru radiation, right? There might be. I'm not familiar with the literature, so I can't tell you much about it.
Some kind of effect in the black hole temperature, something like that?
Sorry?
Some kind of effect in the black hole temperature. Or something.
Well, in these models, for example, you have effects, for example, in the photon sphere on the black hole, which becomes fuzzy instead of being just a line, say. And yeah, you can also have deformations of the black body spectrum. So because you would have effects on the thermodynamics as well when you are doing this game of deforming the dispersion relations. And in fact, there is, at some point we proposed a different notion of dimensionality that is not based on this spectral dimension, that is a bit abstract notion, but we were proposing to use the behavior of thermodynamics to infer dimension, because you know that thermodynamics behaves differently in different space-time, number of space-time dimensions. And in fact, you can find matching results. So when you have this UV running for spectral dimension, you can also see that the thermodynamics of a gas of photons, for example, behaves as in a lower number of dimensions. So yeah, you do have effects on that.
And is there, and one last question, is there any effect on the I mean, if you have a modified theory, if you have a modified theory of GR like the Brand's-Dick theory, in that there's a scalar field coupling. So would the scalar field coupling be affected by this deformation at the Planck scale?
Well, this I'm not sure. I mean, in general, there you're doing everything so that it is covariant, if I am not mistaken. I guess you may introduce further deformations, but maybe I'm not the person to ask to about this. Maybe there is someone who knows more in the audience.
Okay, thank you so much, ma'am.
Okay, let's go to the next question. The next question is from Philip Mannheim. Philip, please ask your question.
Yes, okay. First of all, thank you for the very interesting talk. What you're doing actually may be more general than Lorentz violation. I recently published a paper which showed the following, that if you solve the Maxwell equations in a geometry that's not conformal to flat, which would be perturbations, you find that the propagator takes support both on and inside the light cone. So you don't get null geodesics. The general rule is not that the particles follow the geodesic. The particles follow the normal to the wavefront. And if the propagator takes support inside the light cone, then the normal to the wavefront takes support inside the light cone as well. And that's in a theory which is completely general coordinate invariant and no Lorentz violation at all. Now, that's just a comment.
That's interesting. Thanks for pointing it out.
Okay. The next question is from Norma Sanchez. Norma, please ask your question.
Yes, thank you. Thank you for your talk. In fact, I don't have questions. I have points or comments. And
Sure.
perhaps
Yes,
you can clarify me. So I found it's interesting to this use of astrophysical experiments to test Lorentz invariance or deformations. In fact, no experiments have found any Lorentz violations. So I don't found that it could be, I mean, it's very phenomenological for quantum gravity. In fact, you don't need to invoke quantum gravity to just test if any Lorentz symmetry or deformation of group. I really think that till Planck scale, Lorentz invariance, Poincare symmetry, and so on is a very robust principle or symmetry. And the second point came
Maybe can I
we-
comment on this before you go to second point? Otherwise I forget.
Well, you.
Unless they
well,
are
as-
related, then you want to say all together.
I prefer say it all together.
Okay.
I will not forget. I will not. I can guide you if you forget
Okay.
the question. Thank you.
Sure.
The second point came with cosmology and in what you explained about again the violations or tests for inflation, and perhaps you don't need inflation. I mean, as you comment on that, I want to recall that the inflation, in fact, is very needed, not only for scalar and which have been measured and tested a perturbation, but also for gravitational waves, which have in fact constrained, but also for the correlation between temperature and polarization, electric polarization, which came from reionization of the universe. And that really is a very strong set, a very good point for inflation that not other, models could, in fact, what CMB experiments have been done from COVID till now is to exclude all models which have been proposed to, to replace inflation. Till now, inflation go very well. And I would stress, and this could be interest you, that inflation, what you mentioned and what in general can be tested, or general is enough with a slow roll inflation. But in the period before, and that is grand unification theory scale. You are not in Planck scale, it's grand unification. And what is interesting, is that there is another period of inflation before, which is fast roll, and which is also an attractor dynamically, and that came with features. Some small ripples, and that is very interesting to test with. Irrespective of quantum gravity, but from the point of view of semi-classical gravity, it's very interesting to test with all the experiments on which we have high energy or cosmology. And the third point is in connection with cosmology too, is that perhaps for quantum gravity, the most interesting or most accessible, it could be dark energy, because that is a quantum vacuum effect, which is classical gravitational vacuum today, but it has been sourced in the very, very quantum era and before, quantum gravity is before Planck scale, trans-Planckian, deep in the quantum domain, not only at a fixed scale. So quantum gravity is really in a deep trans-Planckian domain. Trans-Planckian not as a kinematical effect set, but as a truly energetic effect and a domain. And really, I think that concentrating only in trying to test deviation from Lorentz invariance, which is an old problem, with cosmic rays, with all the facilities we have today, is really now appears as a not so wide. It's a very focused, which does not give place to quantum gravity, really. And for quantum gravity, we need for black holes, for, as I have mentioned, for Hawking temperature, which, by the way, in cosmology, Hawking temperature is semi-classical temperature, and in cosmology is for the inflationary vacuum. It appears not at a temperature, but at a length. Inverse, and so these are my points, because I don't see really, it's very interesting, but I don't see here really new progress. Thank you.
Thanks for the comments, because you give me the chance to clarify few points. So let me see if I remember everything. If not, you can remind me.
Yes.
Concerning Lorentz invariance, you mentioned that it is already very strongly constrained. And one has to be very careful when saying this, because you really need to specify what has been very strongly constrained. So the strong constraints that we have at the moment concern the ones that are really strong. They concern the formed interactions of particles. And this has been tested with cosmic rays and other astrophysical frameworks. So it is true that the formed interactions are very strongly constrained. However, this is a feature that emerges in Lorentz breaking theories. Is a feature that does not emerge in the formed symmetries, or if it emerges, it emerges in a much milder way. So these results that are strong constraints, they constrain the deformation of interactions that might arise when you break Lorentz symmetries. The constraints on time delays, which is a common prediction of Lorentz breaking and Lorentz deformation. As I said, at the moment, the constraints we have are around the Planck scale and are affected by the issue of understanding the sources. So I think it is really worth investigating more. And concerning why would you test it, as I said, at the moment, I mean, in the last 10 years, there have been results suggesting that these deformations of symmetries might emerge in specific limits of fundamental quantum gravity theories, such as loop quantum gravity or gravity 2+1 quantum gravity coupled to matter. So even theoretically, at a more fundamental level, there is motivation for that. So, yes. Sorry, let me finish, otherwise then you can. So, I mean, I would say that it is interesting to study this further. I mean, and not be superficial in assessing the relevance or the experimental status of this. Concerning inflation, it is true that inflation does more things than just explaining the power spectrum. And these are things that are worth investigating. Concerning reionization, I don't think you need inflation for that, because that is a process at a later stage. Of course, the way it happens depends on your underlying theory. So if you have inflation, you want it to happen in a specific way. This is something that definitely is worth investigating, whether you can reproduce reionization also in this framework here. So this is something to be studied. I wouldn't be pessimistic in saying that only inflation can match that. And I mean, the theories that have been excluded in favor of inflation, I agree that inflation is very successful. So you need really strong motivations to go beyond it. And this model here at the moment is not as much developed as the inflationary framework. The theories that have been excluded in favor of inflation were not considering this kind of dimensional running or violations of the energy momentum dispersion relation. So I think this is one model that deserves to be tested against the inflationary paradigm. Then it might not work, but it is an interesting observation. I think that you can go beyond. I mean, you might produce what we see in other frameworks. The last point, I agree. I mean, what I discussed here is not just, I'm not claiming that this is the only things we should be doing. Thankfully, we are many people. So many people can work on many different things and work all together to solve quantum gravity. And I agree that, for example, the problem of the cosmological constant or dark energy very likely has to do with quantum gravity. So it is worth understanding that. And in fact, it is a very interesting problem because it is a case where UV physics affects very infrared physics. So it is a UV-IR mixing at its best. And that is very interesting. I mean, I agree that that probably is some effect of Planckian physics there. And I also agree that physics of black hole is important for the study of quantum gravity.
Well, I don't want to monopolize. I just the words. I mean the time of speaking. I just want to answer very briefly, and saying that you don't need, and saying that for quantum theories of gravity and quantum space-time and non-commutative coordinates, you don't need invoke violation of Lorentz invariance or symmetries, and that is what I think must be open. The game in which this Lorentz invariance, deviation, and so on are motivated by quantum gravity. These are is more phenomenological. You don't need really. I mean, you can construct models or even theories of quantum space-time in which you don't invoke this violation. That is the point I wanted to make. And inflation is rather strong. I mean, inflation, as we know, is rather strong. I mean, and as an effective theory, and so there too, I don't think that adding variation of dispersion relations and so on to what we know and tested could add too much for quantum gravity. And I think that, as I said, for quantum gravity, which have not been till now strongly worked, because it's rather new and it's a problem and so on, is dark energy. And dark energy, and we have observation for that, and also for black holes. I think that is a thing in which said new things could arise. And in connection with this, because it was asked last seminar to put references in the, I put the references in the chat, and I have a good news to announce is that my last Transplanckian paper in the I have a Transplanckian trilogy, and my last 20, of this year is have been accepted completely. Is a long paper. Have been completely accepted in Physical Review D, so you can find in Physical Review, and they are about non-commutative space-time, and also what could be tested. I mean, as the remnant of that in the semi-classical regime. So thank you.
Thank you.
Okay, thank you for your remark, Normas, your comments. Let's go to the next question. The next question is from Chi Yu Chen. Chi, please, sorry for maybe incorrect pronunciation. Please ask your question.
No, it's a very perfect pronunciation. Thank you.
So,
Okay, thank you.
So my question is a simple question. So since this is essentially a test of modified energy momentum dispersion relation, and in your talk in the astrophysical context and cosmological context, you introduce a parameterization of this modification. So my question is, what is the guiding principle of choosing this particular parameterization? I mean, you could have different quantum theories of gravity, and they may give you different kinds of dispersion relations. And so what is the guiding principle?
So here, concerning astrophysics, the idea is that whatever modification you have, so it's true that the different theories may give you different modifications. However, in astrophysics, for this kind of studies, you are sensitive to the first order correction, and that is quite, there's not much you can do there. You can have different values of the numerical parameter in front, which is the parameter you are constraining anyways. So the idea there is just to look what could be the effects of the first order correction. So you're basically assuming that the dispersion relation can be Taylor expanded around the inverse powers of the Planck energy, which is kind of general assumption, I would say. Concerning the cosmology, it's the other way around. So there, what you are sensitive to is the UV limit of the dispersion relation, so the highest order corrections. And the one here is just the one that we consider here. Where is it? Yeah, here, this one is just an ansatz. And the motivation for this is that we wanted an ansatz that could reproduce this running of dimension to 2, because this is what you see when you are computing the spectral dimension within full quantum gravity theories. So because you're sensitive to only the highest correction, you know that it has to run to 2 dimensions, and then it should be some power with some gamma there. So this is the motivation for picking these specific forms.
I see. Thank you very much.
Thank you.
Okay, the next question is from Shravan.
Hi, Julia. Thanks for the very nice talk. My question is related to phenomenology. So, as you mentioned about the scale invariant power spectrum in the context of inflation, but I'm curious if you had looked into very small scales, because especially nowadays there's a lot of interest in small scales in the context of primordial black holes, either towards the end of inflation or after inflation. So surely I presume that Lorentz violating corrections would be much more important in the small scales. So if you have some comment, that would be.
No, it's an interesting observation. I haven't looked into it. But yeah, in principle, it is true that the smaller scales are the ones that were even more into the Planck scale early on. So they would be strongly affected by this. So yeah, definitely it's something worth.
Yeah, because there's a lot of constraints on PBH and maybe observational constraints. So maybe some of those constraints can be useful to constrain.
Yeah, you're right. It could be an additional way to constrain it. Yeah, thanks.
Thank you.
Okay, more questions? If not, okay. Philip, please ask your question or comment.
It's a really very general question. All of these different candidates for quantum gravity, are they known to give finite answers?
You mean, for example, you mean fundamental theories?
Yeah, all of them. I mean, they're supposed to replace Einstein gravity because it's not renormalizable. So
yeah, they were built to solve that issue. So this is the case for loop quantum gravity, for Rava gravity. And
okay, so I'm not in the field. So you're saying that they give finite answers to all orders in perturbation theory?
that's what they're built to do in some way or another. Like in asymptotically safe gravity, then you have an asymptotically safe fixed point. So yeah, one way or another, in principle, yes.
Okay, thank you.
Okay, I see one more questions from Giovanni Venturi. Giovanni, please ask your question. Are you here?
Sure, thanks. I actually wrote the question since I don't have much time. I'll be very brief. Did you do a chi-squared fit to the power spectrum? And if so, what is the confidence level?
To the CMB power spectrum, you mean?
Yes, scalar spectrum, the power spectrum, you've got a number of parameters.
Oh, no, we didn't do a fit. We just were searching for which are the values that match the observed values without. So very basic, very basic level of analysis.
Yes, indeed. So basically, if you want to test a theory, you have to do chi-squared fit and see the confidence with respect to the normal situation. So I personally think you can do anything you want, but you should compare with the data properly. Okay, that's all. Thanks.
Thanks.
Okay, more questions? If not, let's thank Julia for a very interesting, very nice talk. Thank you very much. Thank you very much.
Thank you, Julia.
Thank you. Bye.
Don't forget to send us your presentation.
Okay, I'll be in touch with Luca.
Yeah, Julia, yeah, you can send it to me.
Thank you.
So yeah, thank you very much.
Thank you.
very much.
Bye-bye.
Bye.
Thank you.
Bye. Thank you very much.